So this is another video on Advanced Higher Unit 3, and we're going to be specifically looking at errors in practical work, because this is something that you need to be able to identify in your own practical work, why your result might not have been 100% perfect. But also increasingly in past papers, there are lots of questions asking you to explain why a result may have been lower than expected or ways to fix that. So the most important thing for you as scientists to know is that most experiments, and by most I would probably say all experiments, are not 100% successful. And this is quite difficult for people to get used to, particularly if they're used to doing well in exams. Now, it does not mean that you are a bad scientist. It is just a fact. It is not possible to perfectly perform every stage of a process. And the fact that it's impossible means that there's always going to be some errors. It is expected, it is natural, and the best scientists on the planet do not get 100% yields in their reactions because it is impossible. So common sources of error. So one source of error is choice of equipment or access to equipment. So some pieces of equipment are more accurate than others. So always read the methods of experiments and check, could the accuracy be improved by changing the equipment? Things like pipettes and burettes are much more accurate than using syringes or measuring cylinders because they're designed to be more accurate. But even amongst burettes and pipettes, there are grades of glassware. So if you are able to, you should be using grade A glassware. It is the most accurate. However, most schools will not be able to afford grade A glassware, and so will have grade B or lower. And while there is the expression, a bad workman blames their tools, when it comes to accuracy, if your tools are not able to work to a degree of accuracy that is needed, then they are a source of error. So if you are ever asked, remember, if you're measuring out a volume, you want to be using a burette or a pipette if possible. And even if it says that a burette or a pipette is being used, you could always say, make sure that your glassware is grade A, as that is the most accurate. When making solutions and dealing with volumetric analyses, the biggest issue is with standardization. Remember, you should only ever make up standard solutions of primary standards, and then all other solutions should be standardized against your primary standards. So every non-primary standard should be standardized. So it is important that you go back and make sure you know what are the 6 or 7 primary standards that you need to know for Advanced Higher. Most of your common chemicals cannot be used as primary standards because their GFM is too low. So one example would be sodium hydroxide, and sodium hydroxide should always be standardized with oxalic acid. Commercial acids. Now you should be able to trust a commercial acid, and most people do. However, if you really want to confirm your accuracy, you should be standardizing hydrochloric acid, sulfuric acid, nitric acid that you buy against a primary standard like sodium carbonate. So you do a titration. So if you see that chemicals that are not primary standards have been used in a volumetric analysis, one way the experiment can be improved, or made more accurate is by explicitly saying that those non-primary standards should be standardized. And if you can give examples of chemicals that could be used to standardize them, that's even better. In a volumetric analysis, particularly a back titration, it is important that you do a control, because a control is a way of testing your methodology. So what you would do in a back titration would be to trial your method with either a sample that contains an exact quantity or a 100% pure sample. So if we're talking about using an exact quantity, that would be using a pharmaceutical grade sample of aspirin that has a specific dose in it, or a vitamin C tablet that's got a specific dose in it. Or if you're doing something like marble, you'd want to test it with some pure calcium carbonate. If your method is perfect, your final values should give you exactly what you're expecting from the control. So if you can say that, you know that your method is accurate. If you can get the exact value that the control should have, you can say that your sample, that your methodology is good. So you can always do a control. And it's just checking the robustness of your method. When it comes to gravimetric analysis, some of the sources of errors would be not weighing by difference. So if you do not measure the weight of your weighing boat or the container that you're storing your sample in, you will have to manually weigh your solid each time. Every time you transfer a solid from one container to another, you will lose mass. So making sure that you're weighing by difference and know the mass of your container is a way of reducing error and improving accuracy. Not reaching constant mass. Well, any time that you're doing a gravimetric analysis, you need to make sure that your final compound is dry. So you need to keep, put it in an oven and keep reweighing it until you've reached constant mass. More so than that, you also then need to keep it stored in a desiccator because that will avoid it regaining any water. So remember, do your drying in an oven, store your sample in a desiccator. Another thing would be, why would you have a lower than expected percentage yield? And again, what I'm going to stress to everyone is that it is impossible to get a 100% yield. It is impossible to get a 100% yield, even for the most simple reactions. Every single step you do causes some product to be lost. The more steps that are involved, the lower and lower your yield will become. So why would you lose product? Well, transfer is one of your biggest sources. Every time you transfer a solid or a liquid, you always leave something behind. Particularly with solids, there will be some solid left in the flask in which the solid was made. There'll be some solid left on the filter paper or on the funnel that you used to filter it. There will be some even on the spatula or on the weighing boat. Liquids are much easier to transfer than solids, so if you are doing a transfer, you can try and dissolve it. Similar to when you're making a standard solution, your first step is to dissolve it before putting it into a volumetric flask. But you need to make sure, if you're dealing with liquids, that whenever you pour a liquid out, you also rinse it out several times or wash it out several times to get the transfer. But transfer is the biggest loss of product, and it's natural. It's impossible to get 100% of material transferred from one source to another. You'll always lose micrograms or milligrams, which will make a difference. The other thing to remember is that if you needed to do a purification, if you needed to do a distillation, if you needed to do a recrystallization, purification methods are not designed to give you 100% of your product pure. They are designed to give you pure product, but you will always have some impure, you'll always have some of your compound left behind with the impurities. So every single time you do a recrystallization, a distillation, even using a separating funnel, because of the equilibrium coefficient, you will always have some of your product left behind, and you're sacrificing product to end up with something that is very, very pure. And this is something that a lot of people struggle with. Well, I purified it. Why am I not getting 100% yield? Well, it's because you can't. If you do a purification, it's impossible to get 100% of that compound pure from doing a purification technique. Another situation you might find yourself in is having too much product. Now, this should never happen. If you get a percentage yield over 100%, you have done something wrong. But it can always be corrected. So if your sample is too heavy, what you should first try and do is dry it to constant mass, because water or solvent always adds mass. So check that you've dried it to constant mass. The other thing to do would be to check its purity. So do a melting point analysis, do thin layer chromatography. If your compound is not pure, then what you need to do is a separating technique or a purification technique that will remove some of the compound that is not what you want from your sample, and it will bring the mass back down. You can always find ways of dealing with a situation where you've had too much product. It could just be that you've not had enough time to do the purification or to dry to constant mass in class. But if your percentage yield is too high, the steps to take are try drying to constant mass and checking the purity, and if need be, do a purification technique. So that has been a go over some of the errors and how to explain why they arise, and in some instances how to prevent or improve the accuracy of your experiment. One thing I actually want to say just as a final point is that repeating an experiment and taking an average is not considered something an advanced hire that improves the accuracy of an experiment. What that does is that improves the precision of the experiment. If you repeat it and take an average, it shows that an experiment is reproducible, but it doesn't actually tell you anything about whether or not your result is accurate. Accuracy is determined by using a control and by checking the purity of your samples. Precision is improved by taking averages. So if you're ever asked about accuracy and you write just repeat and take averages, you won't get any marks for that. You need to talk about some of the techniques said in this video. Okay, so that has been sources of error in experiments, and I think that is our final video for Unit 3.